Now I will pass the word for the session chair of the first talk. Professor Leandro, please.
So let's start with our event today, and our speaker for today is Felipe Rosa. Let me just add. Oh. Felipe was born in Porto Alegre, in the southernmost Brazilian state, Rio Grande do Sul. He holds a PhD in microelectronics and Bachelor of Computer Engineering degree from the Federal University of Rio Grande do Sul. Felipe participated in the BRAFTEC, studying in the Bachelor's of Engineering, Microelectronics and Automation from July 2012 to July 2013 at the École Polytechnique Universitaire de Montpellier. In parallel, he was an undergraduate research intern at the Laboratoire d'Informatique, Robotique et Microélectronique de Montpellier. In 2015, he was accepted to a one-year exchange at the University of Leicester at the postgraduate level in the engineering department. He researched the reliability of many core embedded systems using virtual platforms. Additionally, during this period, he worked as a software engineer at Impera Software Limited, incorporating performance estimation tools in its commercial engine. Felipe is currently a senior modeling engineer at ARM Cambridge, UK. His main work projects include system interconnections, example CMN 600 and CI 700, and platform integration such as Total Compute FVP. Thank you, Felipe, for accepting giving this talk at the CASSW, and the floor is yours.
Thank you, and thank you, everybody. Thank you for the invitation from the committee to invite me to be the first presentation. I'm gonna share my screen now. Share my screen. Hopefully, you'll be able to see my presentation. So today I'm here to talk in my name and not represent ARM in any way. Most of this work was developed during my bachelor degree and PhD, where we had some collaboration with the company, but not supported fully by the company. So just a disclaimer. So the point of my talk today is to demonstrate that people can use high-level simulation to do a large number of simulations in a short time of period of time without having to research a lot of cluster or AWS time. So that's my point today. So why I'm talking about FVPs? So this is basically my career path in the last 9 years. Since I met Dr. Ricardo Reis and Luciano Ossa in 2012, I started working with them. And since the first day, I work with virtual platforms. I work with several virtual platforms in different levels, different architectures, from IoT to large-scale systems. So I think I have a good enough knowledge on this background so I can pass to you and help you to have new ideas to use virtual platforms to accelerate your research or do a better presentation during a class or anything that you can use simulation. So I work in ARM for the last 3 years, and that will be the last part of my talk, trying to talk about what I'm doing now and the project that we are doing with some partners that are public. So let's think what we are trying to achieve. Let's take the concept of a smartphone. A smartphone, it's a consumer good that takes several steps to reach the final user. And usually, if you're thinking in sequentially, this is not the reality, but if you think sequentially, you can have concept, you need to have a specification where you have a document describing what you need for this hardware, have the hardware design, a lot of hardware verification, then you're gonna have the tape out, and then on a conceptual way, you're gonna have the software bring up after you have the hardware. But that cannot be the reality because we cannot wait that much time to start developing the software. So later in the 90s, people started using RTL simulation to try to bring up simulation early in the development cycle so you can start using your new kernel or new way earlier that's necessary without having the actual hardware. And that's the whole concept of using software to simulation to start earlier the software development. So, for example, if you choose to use RTL, which is a proven and well-known technique today. You can have the whole hardware simulated, and that's good. You can have a lot of precision, but what's the drawback to have this? So usually RTL is very low. You need to have the actual hardware present. You have to have the commercial IP, the commercial interconnection, everything ready to you. Usually it's not that easy to work with RTL. You don't have any, you have some debuggability, but it's not on a hardware. You can access the memory, but usually don't know the concept of the memory, how the memory is structured inside a large system like the Linux. So I have virtual memory, multiple pages, and sometimes virtual machines on top of the Linux. So work on this setup, it's possible, but takes a lot of research. It takes a lot of time. So this, I'm separating 5 categories of simulation. That's not the reality. There's many others simulation tools available in different areas you can explore. So I decided just to simplify in 5 different categories. You have electrical simulation, usually your spines, where you simulate your transistor, maybe few transistors, and you can have for analog simulation and process that. We have the virtual, which are a cadence tool that's a default RTL simulation tool that you can use. Usually it's very good to a very lot of VHDL simulation. You can have even the cell synthesized, everything to your simulation is very precise, but the speed is not that great. So usually I got this from the ARM website, so we can have up to 50,000 instructions per second on a big ARM core on a commercial tool, which is a lot, 50,000, but not a lot that you can bring up a full operational system or a rich environment. In the last years, people in the 20 years, they started developing new tools, usually trying System C to have some cycle created, but destroying some parts of the model. So you don't have the pipeline model, don't have each individual cells connected. So this bring you to some thousand of KIPs or couple MIPS, which is good enough to have Android boot in a couple of days, and which is still not good enough. So people continue to develop, and they create microarchitectural simulators, which the best example I can find is Gene5. Gene5 is a C++ hardware description. You have cache pipeline, reorder buffer. Everything is there, depending the way you simulate it, but you only can get from 0.3 to 2 MIPS when you are not simulating the actual pipeline. So it's good, but not good enough. So how you can develop software on the fly without have this huge backlog of simulations? So in the last 10 years since I started to work with virtual platforms, this concept of simulating or emulating just a programming view, so you can create the software way before you have the hardware, had emerged. There are many tools available. One of is not open source, but free license, depending on your university agreements. It's Impera that I work with them for 8 years. So they are a best free example what you can do. And usually on this concept of virtual platforms, I'm talking about some System C until programmers view. There's many different virtual platforms. Virtual platforms is not one thing. It's a group of simulation that's fast enough that you can emulate a complete software stack and bring some rich environment to your operational system. So just recapping, virtual platforms can be anything like that. You can just need to make your software believe that's working on the real hardware. And that's the hardware could be abstracted. You don't need to have a pipeline registers which the software interacts, and that's the most important thing. But there's the whole trade-off between how much precision do you need, how many accuracy that you need compared with this precision. Seconds, milliseconds, or milliwatts, and exactly what you need to have your simulation. It's how you're going to define which virtual platform you're going to use. So if you have a virtual platform, which is the modern way to develop or bring up a system, you can have a virtual platform description before we even have the specification. So we can start doing the virtual platforms when people are still drafting the specifications, because as we don't model everything, you can have a lot of blanks on your actual virtual platforms. You can abstract the new pipeline feature if we are not emulating pipeline. So we can have a bring up earlier. So in this example, you can start bring up your code several months before you even have the RTL ready. And that's the whole goal of on commercial tools, on academia can also use that. So we can skip all this. And if you're not a company, you don't want to bring up a software because you want to sell smartphones or IoT. What's the point of using virtual platforms? Usually virtual platforms are easy to model. They don't need a highly specified engineer to model in System C. You can model almost all the platforms that you can think about. So they are several mods, like there are MIPS, ARMS, x86, PowerPC, RISC-V. They're all available in different ways, and you can model and mix them together. Usually, the simulation targets thousands of MIPS, but if the system is larger, of course, it'll be smaller performance. But usually, on the hundreds of MIPS until thousands of MIPS, depending how big your system. Developing virtual platforms is super easy and is super fast, and that's something that we need in academia. You want to start developing your new mapping, your stake, or your new file, or your new OS change that you want to publish, and you can do this on a virtual platform on the fly. You don't need to simulate on RTL. That takes 2 days just to bring up the Linux, and then you start doing your work. And most important, because it's a C++ abstraction, you can add code, everything that you want from that simulation. You can get a number of instructions. The instruction, stop the instruction on a particular point. I'm gonna show some examples of it. And you can use this powerful environment to create any type of research inside the limitations of virtual platform, which is also something I'm gonna talk. So this is my first example, my actual research that we did in 2012, 13, 14. So what was the problem that we were trying to figure out and solve? So how I can profile an application, an embedded application, as early as possible and extract some cycle and power estimations to see if a code is improving or not improving, depending on the changes. So that was the problem that we were trying to solve in 2012. So we investigated hardware. So we can have the actual board. I have the board that we are modeling, but it's the true data, which is awesome. I can have the number of cycles that each instruction takes. But the problem is we need boards, and they cannot change. I cannot change the cache in the board because it's already been fabricated. I cannot do that. So the other option, we tried RTL. RTL is as precise as the hardware, depending on the configuration you have, but the cost is large. We need a lot of machines. You have the licensing, and you have a lot of problems debugging, because if it's so slow that you need to bring up applications, you cannot debug on the fly, and that brings problem to create your software and work on the RTL. Also, most of the time you're gonna need a complete IP, a commercial IP, and these are restricted by NDAs, and your university may be trying to get an NDA with ARM or Intel, and that takes time. So usually if you have the actual IP, it's way later when you start your research. You can use FPGAs. FPGAs are nice, they are flexible. You can do anything you want, but you still need to do all this modeling, usually in RTL language like Verilog or VHDL, and still it's a lot of burn in your research to create just this system that you want to model and then start your research. So we choose virtual platforms because they are very fast. They are hundreds of thousands times faster than RTL, but there's no concept of power or cycle on this. So that was the whole point of the research. So how we bring up an initial cycle estimation. We don't want to know how many cycles the application takes. We want to know, I estimated in a region of neighbor of 10%, how long we want your application gonna take, and then change the application, change the matrix size, for example, and see how long this will take after that. So for these examples, we use the OVP Syn, which is the free license tool from Imperis, which is a virtual platform company from Oxford. So how we did this cycle estimation or power estimation. So every time that we fetch an instruction from the simulation, we decode this instruction on the fly. We check which instruction we are trying to execute, and we have a hash table that you can access information about how many cycles it takes, and if it's after load, after store, how many cycles take. All the information is embedded in a hash table. We read this hash table, and we have the number of cycles. that's not that difficult to think about, but implementing that consistency is very slow and take time. So we could implement this on a virtual platform in a month, less than a month, without much experience. And that's what we did. So we decided to test, well, we have a virtual platform that runs thousands of MIPS. How precise is that platform? So we bought the same board that we had been modeling, this board from ST, and we run the same software on both, same binary on both platforms, the FEP, OVP sync with cycle and power modeling against this board from ST. So I'm not sure if you can see it's that big here, but this is the cycle count for the model, the cycle count from the actual board, and this is in points of percent, how big was the error. So if you can see, we have 39 applications from IoT, industrial, automotive, several applications that are in different benchmarks, and we are combining this 39 sets. You can see that the average is below 8 in 33 of the 39 applications, and the worst case is 11% of mismatch. And for something that is as early as we are doing, 11%, just to understand if you're improving the software or not, it's more than enough. So you can have your software ready when the hardware is available and everything is checked and the performance is improving. And then you can move to a board FPGA where you can focus on performance optimization. And that was the whole point of this research. But we are talking about virtual platforms. So we can create this tool. We can have all these tools implemented. Later on in my career, I implemented this in Paris, which is the commercial tool. We even feedback this cycle estimation to the timers. So the timer was dilated depending on the cycle estimation. So even the Linux timing side was a little bit more estimated, so closer to the reality, but mismatched by 8% in average, like I showed in the results. Okay, that's the good part. That part was published in these papers here. But what is the limitations? What things people need to think about before they are doing this on a virtual platform? So first of all, this model was single and in order pipeline. So our pipeline was 5 or 6 stage on that hardware. So it's a very simple pipeline. There's no much reordering. You don't need to do anything. You always know the order of the instructions. That's the whole point of the IoT embedded applications. And it's a single issue, or sometimes it's a double issue, but it's a single execution. So you always have one instruction per time. It's not like a big A75 processor that have 5 instructions being executed at the same time. So this predictivity of how many instructions are executing makes possible to create this model where we can fetch one instruction per time in the OFP and have a very good precision. If you scale that for a out of order SCAR pipeline, the results will be way different. There will be a lot more work to create a usable cycle estimation. I know that someone ported this work for an A9 with dual pipeline, but I don't know if they continue the work later. Also, there's variability even in the hardware. The hardware has instructions like div, emult, where the cycle depends of the operators. So there's the division has early termination, the multiplication has early terminations. So later we add this information to the model, we aggregate this and try to define a little bit closer. So we reduce even more the mismatch between hardware and FP. But it's something that you need to predict and need to understand. If your tool has a skew about division or multiplication, your error could be larger, and you need to understand from where this error is coming from. So that model is portable to any application, but you still need to have a cycle or a power information. You need to have access to the RTL on a board so you can see how many cycles each instruction takes, or how many power you're going to take for each instruction. You need to have this information. This is not usually available for any commercial tool or any commercial processor. And for sure, you cannot use this tool for real-time or critical applications. On real-time, you need to know how many cycles everything going to take. So you need to have the predictability to execute that. So you cannot use that. So you need to understand that if you are using for embedded applications that can be loose-timed, you can use this tool. But if you have other times of real-time, you cannot use this tool because you're going to have skewed results. And that's the things you need to understand about virtual platforms, the limitations, and what is good on it. So this is the second example I'm gonna give you. Just checking the time. So the second example is based on my PhD from 2014 and 18 with Dr. Ricardo Reis and Luciano Ost. So the problem here, we have radiation everywhere. Everywhere that you are on this planet or out of this planet, you have radiation. And with the decreasing size of semiconductors from 180 nanometers to 10 nanometers, 8 nanometers, the amount of energy injected by a single neutron reaching and striking your semiconductor substrate causes enough energy to flip things inside your CPU. So a single neutron can attach to a flip-flop, for example, cause an energy spike and change the flip-flop's value. And you think it's just one flip-flop, and this is going to go away in the next cycle. But this causes a bunch of errors, and they need to be assessed as soon as possible. So that was our PhD idea. How we're gonna check how your software behaves under radiation-induced software errors in an early development phase for multiple systems as early as possible. We don't want to wait until the hardware is there so we can run an Android stack or a multi-core MPI, OpenMPI, or OpenMP application. So we want to be as early as possible. So when the hardware is there, we can just have some idea how the software will behave under infrastructure software induced reliability. So again, we study what we can do. We can have board-oriented approach. You can buy the boards, put on the radiation, and see what happens. That's very precise, but usually cost times is per hour. The radiations per hour. You need to have people on site, and it takes time. Each evaluation takes days, sometimes weeks, and each board at the end will be destructed. So you have a huge amount of boards and resources to do this type of investigation. We have some idea using RTL or gate level simulation, which are very precise, but again, there's not enough power on this, so we can develop the amount of simulations that we need to reach a good investigation. So end up scrapping the RTL. We try to think about consistency, but the problem is there's a lot of consistency models, but usually they don't communicate each other. We can have a CPU system C description, but usually you don't have the interconnection that you want in system C, and have another interruption controller that's not in system C, could be another language, and you try to Lego and mount this. Everything is sometimes very complicated. So we decide to use the virtual platforms and see how it can be used as early as possible and as fast as possible. So for this purpose, we decided to use two different OVPs. So our objectives on this project was, we want to target a modern architectures like ARM v8, the newest core that we could find. The idea was to have multi and many cores, from one core of ARM M4 to 100 cores of another ARM architecture, an ARM A9, for example. 100 cores from 1 to 100 cores. The complex workloads is one of the main points. We want to use OpenMPI, MPI, and other high-performance parallel applications, and that was the key point for our research. And also, we want to have a Linux kernel to be realistic, and this kernel doesn't need to be modified. You don't want to have a special simulation kernel that we modify just for that one, and then when you need to move to another kernel, we need to do a whole lot of work to port our changes to the new kernel. So that was the premise of our research, and we choose these two different virtual platforms. Gen5, which is a well-known architecture development virtual platform. It's cycle-created, quasi-cycle-created, depending on who you ask. It has microarchitectural elements, has the pipeline, it has a cache model, which is well-known, so we can create a very good cache model on that one if you want. As again, very slow. The models, they can represent a CPU, but they are not exactly that CPU. They have limitation on how precise you can model the Gen5, because you don't have all the information how to implement an x86, for example, or even if you have the information to implement that on Gen5, you're going to need to change how the Gen5 was modeled, because there are limitations about how the classes interact in Gen5 and how the pipeline was developed 20 years ago. So you need to think about, you can add things, but there's not that easy to add this. And also Gen5 is not that scalable. Its simulation takes 10 gigabytes, 15 gigabytes, depending on the size of the system. It takes days. So you can run a lot, but not that much. And the opposite side have the highest possible simulation, which is the OVP simulation from in Paris. It's fast, it's easy to model, it's scalable to thousands of simulations, but there's no cache model. It's a gist-based simulation, which means that it fetches one instruction from the code, it decodes, and executes on the host machine. It doesn't simulate the pipeline, the fetching, the issuing, anything like that. So there's a lot of abstraction here between both. And it's a completely on-time simulation. You don't have the control time. Usually the time is one cycle per instruction, so just have a notion of cycles, but it's just to make the timers go on and triggering later. So on this injecting files research, we have to define things, well behavior, and they need to be consistent. So what we need from any virtual platforms, in this case of VPC and G5, what we want from these platforms. So we want them to access the code of the CPU, get the registers, inject the fault, see how the processor behavior, extract the information, and see how the information compares with the execution without errors. So you need to have all this level access to do this. And usually on RTL, we can do that. We can add extra hardware on that, but that's a lot of work and that takes a lot of time. That's just an example of our simulations, how many components we have and how we extract them from Gen5 and OpenPC. One thing that usually people don't think about, but is a very good use of virtual platforms, because you can debug anything, you can access any information, you can have very rich amount of information from any application. So usually people have 2 or 3 classifications on reliability papers. Usually they have completed without errors, not completed, and completed memory errors, because you can only check if the CPU is finished on the right moment, or if it doesn't finish, probably it's a seg fault. And if it's not a seg fault, probably the memory is dirty, and that's what you can do. On a virtual platform, you can check each register. So you can check individual register that you want to check, not all the registers. You can check the memory. You can check pieces of the memory that you want to check and exclude the others one. Have a rich environment that you can do any type of classification, and that can make you a very good use of these tools, is to create specialized classifications just for you. You don't need to use the generic ones. You can use your own classification. That makes a lot more rich of information for your paper or your development of software. So for you that are not used to reliability expressions, this is the usual flow of a simulation. So you have an application, a target application, the operation system. We compile that. We run on a virtual platform, Gen5 or VPC, without inject errors, because we need to know how the application behaves when there's no errors. That's the whole point of reliability assessment. We extract a lot of information and we save this. And we use this information that we just extract to create faults, because we want to create faults within different moments. For example, in our examples, we never inject faults on the Linux boot. We inject faults after the application starts on the Linux. So we need to know when the application starts, and we can do that with the virtual platforms, because we know what is running on the platform, and we can exactly communicate, this is the start of my application, and inject faults after here. So that's very useful for targeting exactly what you want. After generating the faults, you need to inject the faults. And if you need to inject faults, usually each simulation is independent of the others. The simulations are independent, so you don't need to sequentialize them, and that's we're going to discuss in the next slide, how we can improve virtual platforms to an even greater scale of simulation. Then you aggregate all the information, and then you create reports. We could create reports like these ones, the author graphs. We create different graphs. We create even visual explanations why they are happening here, and that's all possible because virtual platforms can have you a great deal of information for you. So on this scenario, we decided to use different kernels. I think we had 3 different kernels on this PHT. Have 45, at least 45 different real workload from high performance benchmark sets. For example, we use the Rodinia benchmark, which is well known, and the NAS parallel benchmark, which is the NASA benchmarks for high performance computing. All these are parallel, and they try to use as many cores as they have. Most of them are OpenMP and MPI, so they are well-known parallelization libraries. So for each time I have one application for one kernel with one virtual platform, I need to run this 8,000 times to get a good statistics for each fault injection. That's why you need performance, because with reliability, you usually need to take a lot of runs to have a good probability statistic. And that's a lot for RTL. For example, 8,000 RTL simulations that take one day will be a lot. On the whole PHT, I think we took 3 million fault injections, and at the end we had like 2 million simulation hours. This was thanks to the University of Leicester. They had a high performance computing there, they call Alice, and they have like 5,500 cores. I was able to use up to 1,500 cores, more or less, sometimes 1,000 cores at the end of the day, and use all this for fault injection. That's why we could get to 2 million simulation hours in 6 months or 1 year. For all these experiments, we have 3 different virtual platforms fault injectors. We have the OVPSync, which is the virtual platform instruction level, no time. We have the Atomic G5. The Atomic G5 is a G5 that has a pipeline model, but it's a simplistic pipeline model. Usually it's 2 MIPS. It's faster than the other G5, the classical G5, but it's not that fast. And they have the classical detailed G5, which takes 0.3 MIPS, 0.5 MIPS, and has the whole cache modeling, the whole pipeline modeling. It's very precise for microarchitecture exploration. So how we could increase a little more, because you have to do 3 million of simulations, how we can improve that. So we decide to first checkpointing. So with checkpointing, you divide your application in, like, say, 5 period of times, and you do 4 different checkpoints. And with that, you can just restore the checkpoint for the fault inject that you need. For example, if you want to inject faults here, you can recover here. You don't need to execute all this boot and the application installation. You can start here and inject your fault here, and that saves a lot of time. In our experiments, doing checkpoint saves 50% of the simulation time. And that's good, but was still not enough for us, and we had to improve even more on that. So we decided to use that supercomputer, but the problem is usually supercomputers have a NTFS shared repository somewhere that's mounted in a different CPU, and if you try to access everything from your home node, it doesn't work. So we have to create a scheduling and dispatching unit using the ILC queues. So we're gonna create a job that takes 1 day, and this job we're gonna do a lot of simulations sequentially, and we're gonna divide our 8,000 simulations in as many packets we can, and send this to the server in different queues, so we can maximize how much simulation we have in parallel. So we can have up to 1,000 simulations in parallel with different applications, because they are all independent, and we have a queue to manage that in our server. So that one of the tests that I did on PhD was how to create this. And one of the things you need to think about is if you access remotely memory, it will be way slower than accessing local memory on your executing node. So usually it's better to copy everything from your home node to the local machine, the server machine somewhere in the cloud, and execute that locally, delete everything, and copy just results. And that it took a lot of time to figure out and finicky, and sometimes it doesn't work, but after it working, you can dispatch thousands of jobs in parallel and have the as performance as you want. So this is just one example of the simulation time. So on the first column, we have this smaller simulation time for each virtual platform. For the smaller Rodinia application, which was smaller than the NPB, was like 100 million instructions, 200 million instructions. It took 4 seconds on the OVP 11 seconds on the Gen5 atomic, and 30 on the classic Gen5. And if you scale this to the MPB, you take billions of instructions, sometimes hundreds of billions of instructions. We couldn't run the detailed version on the NPB because it's too big. It took more than 1 day for its simulation. So we had to restrict to the Gen5 atomic to have at least some results. So the smallest simulation was 163 seconds, and the largest one was 42,700, which is almost 12 hours. And you see, as big as the simulation grows, as faster the OVP sync goes, because the OVP doesn't need to have all the context for the reorder buffer, the pipeline, the raster naming. So as longer the simulation goes, the G5 is a little bit slower, and the OVP is the other side is faster and faster and faster, because when you translate one instruction, this instruction goes to a dictionary, so you don't need to translate this instruction several times. You can use a hash table. So as much instructions you decode, as fast as you go. So after some time on OVP, you reach your perfect simulation point at which you are 200 times faster than Gen5 atomic. It could be thousands and thousands of times faster than Gen5 detailed. So this, I'm not showing 3 million of simulation fault injections on this paper on here, but we're just saying that if you check all the results, OpenMP was worse than the MPI, and we got thinking, why the OpenMP is worse? Why the MPI is better if they are sometimes the same application with different parallelization techniques? So just a parenthesis, I'm going to explain what is the difference between G5 quickly. So the G5 simulates the pipeline. Each instruction is fetched. There's a cycle. Everything takes on this cycle. On OVP Sync and all JIT-based engines, you don't have this ticking idea. You have a series of models that need to run on the same CPU, on the whole CPU, and you need to divide the time to execute that. So, for example, here you have two processor example. You have processor 1 and 2. So processor 1 executes, it stops, synchronizes with the whole simulation, and then processor 2 executes. Okay. And then after a fixed amount of time that we call quantum, this processor 1 resumes, processor 2 finishes, saves all the context you need to do, synchronizes processor 1 and the other models, and starts again. And this cycle here happens all the time. So you can have the quantum as larger or as small that you want, but if you think about it, the synchronization point where processor 1 talks to processor 2 is when they switch context. And you have to take this in mind when you see the next example. So here we have the OVP sync running different time slices. So if you have a time slice, or in this case, the quantum size, changing from the smallest as possible, which is on the right side, to the default one, you see that the results change drastically just by changing a small portion of the time slice, just reduced by half, have a lot of information that you lost. You can see that changing the quantum will affect the reliability, and we need to investigate that more, why this is happening. So why this happened? When you have an OpenMP application, usually you're parallelizing the for with a pragma, and this for usually synchronize at some point. So all the for need to synchronize at some point and see what happens and go to the next stage of the OpenMP. Because you have a quantum that is a fixed amount of time, or let's say 100,000 instructions, your OpenMP, you're gonna execute all the way, and when you finish, it doesn't have how to jump to the next CPU because the model doesn't know that your OpenMP finished. So the synchronization point of OpenMP is gonna still be waiting for the synchronization and execute the whole till the end of the quantum. When the quantum finish and the processor synchronize, the OpenMP from the previous simulation, the processor number 1, you're gonna see, I finished this, I can go to the next step. But the problem is that processor is already finished, so we need to wait for the next quantum while the processor 2 executes. And processor 2 executes until it finishes the OpenMP part. And then you're going to say, I need to wait for process 1, but process 1 is not synchronized yet because it didn't execute yet. So we have a lot of quantum time or simulation time that wasted just waiting for the synchronization. And this depends how small your application is. This example, we run with few applications in Rodinia, and we figure out that by changing the time slice, we could have a better OpenMP accuracy that we had before without losing that much of performance. Because when you simulate the time slice and reduce the time slice, you have more synchronizations, and more synchronizations mean more time doing memory moving, and then you lost some speed on your performance. I'm going to show some examples of that. So here you can say, I change the time slice from default to 10 times or 100 times smaller, and you see that the behavior is almost identical to the Gen5 atomic, which is our point. We don't want to mimic the detailed because we don't have all this precision, but we want to mimic the atomic version. And you can see that's way closer than it was before. So here we have a lot of mismatch, and now it's way closer to what the reality on the Gen5 atomic. So we run all this information and rerun the applications and got a way better accuracy compared to the Gen5 atomic. The Gen5 detail was a little bit worse, but the point was not mimicking the detail because the detail was executing more structures, not because of the quantum simulation, but because the cache delay, the pipeline delay. So when we reduced the number of instructions, it got a little bit worse compared to the detailed, but the actual simulation performance and the simulation, the software behavior was closer to reality on the Gen5. So these are just the bands of simulation speed using different simulators and different software stacks. This on the left here is the Rodinia, and this on the right are the NASA applications. So we can see that the average simulation for the top end from the small OpenMP to the large MPI was 250% of improvement just by increasing the application. By reducing that time slice, we got 5 times lower, but still it's way faster than the Gen5 atomic for the NASA and way faster than the Gen5 atomic for the Rodinia applications. So you can see that's a lot of improvement here. And we couldn't even run the atomic for the NASA because they're too big. So with all this power, what we can do with this power? So we can execute these days software stack for autonomous driving, which is huge and takes a lot of simulation. And we can execute that and inject faults on that. And that's the end of my PhD and the continuation of this work on the lab. So with billions of instructions, just for executing one frame of one of these applications takes 10 billion instructions, 100 billion instructions. How are you going to execute a whole software stack that takes trillions of instructions on a simulation? On RTL, usually going to take a month, maybe 2 months. On a FPGA, maybe 4 weeks, 3 weeks. I don't know. We never did that. So it opens the possibility to do a lot more investigation if you can focus what you're doing and how you're doing the fault injection. So that was what we're targeting, the final application and how it works. So for this final example, we are comparing the Gen5, the OVP-SIG. We have a library called LibVision 2, which is a visual odometry. Visual odometry when you have images, and by being 3D images, the car can say, I'm going left, I'm going right, and knowing where the car went in the past without having GPS. The whole purpose is not having cars using GPS, but tracking where they was at the start and where they are now, just by seeing the roads and seeing the difference between the landmarks. So for one application that we got 2 different applications. They are same library, and one set has 920 frames and the other 400 frames. So the car moves through for 430 frames, and it has a rule that has to follow and has to verify which rule it just followed. And for example, just for comparison, the OVP takes 6 minutes. Gen5 atomic, not detailed, take almost 2 days. In the time that I executed Gen5 once, I can do the whole fault injection 8,000 times with OVP-SIG. So that opens the opportunity to understand how this software that's very complicated, state of the art, they're going to behave under fault without without having a supercomputer with 500,000. You can use your own desktop machine. So this is the two frames. This is the sequence, what the car should do. These are the pictures, and these are what the car is doing. So the first one, that's set 11, it needs to go here and go back. And the other car starts, go around the block, and returns to the same point. Shouldn't be that complicated. And how imagine that a single fault injection, a single register bit, going to be changed in one of these simulations. We execute that 8,000 times. And you can see this is set 1, where the car is going this way. You can see that one single bit flip in one register, that's not the PC, because if you inject in the PC, the car is going to die way earlier than the simulation. It just stops here. Just on the data, your car is going to think that was 10 meters apart from the other worst case. So I think the final destinations here on dot lines, this was the expected one without faults. With faults, a single bit flip on one register, you can have cars that I think are 10 meters away. And this case is even worse. I think this one from here to here is 15 meters of span that the car could be. Of course, the cars have other options. They have GPS, they have different cameras, and they have different ways to know they are not in the right position. They are not 10 meters on that way, on the other side of the lane. But that's one of the applications that we use today on cars and could be subject to this with a single bit flip. And that's what we could explore with virtual platforms, because they are fast enough to do all this simulation. So a single bit flip causes all this. So what's the takeaways from fault injection? Fault injection, you can be as fast as you want, and that's the point. But what's the main drawback? The main drawback to virtual platforms is that I cannot tell you how exposed your hardware is. I cannot tell you the car has one fault in 100 hours, 1,000 hours, 1 billion hours. I can tell you how the software behaves under fault. That's clear. But I cannot tell you need to protect your car in this way because you have to have 1 billion hours of interval between faults. I cannot tell how many faults you're going to have in one day, one in a year, but I can tell how the software is going to behave. And the other drawbacks is depending how your microarchitectural simulator works, how big is the pipeline, which the pipeline is correct. Then it depends if you are trying to show that duplicating the pipeline, for example, works. You need to consider how the pipeline was modeled, and it's a virtual platform, so there's abstraction. You need to think about that. If you are trying to show how cache ECC you're going to help on this particular case, you're going to have a good cache ECC model, and you think about that if the cache model is good enough for it. If you're trying to change the order buffer, you need to change the order buffer and check actual hardware implementation follows that. All these considerations need to be followed. So that's my current work. So I work on ARM, creating large platforms and bringing up them with software guys as early as possible, way before I have any smartphone or infrastructure platform available. So how you are a company, you have up a new smartphone, a new server. You want to bring up your server. You don't want to wait for the FPGA to be ready. You want to bring as early as possible, and that's proven to work today. You can use virtual platforms. You can bring up your software, have the Linux, have the Android all running before, test the new features, check if the architecture is compliant with your software, and that's awesome. Sometimes we have simulations that run same on the virtual platform like Android. We run Android every day. Sometimes the Android takes 5 minutes, 40 minutes on the FTP. If it is the newest, best Android, it will take 40 minutes. On the RTL days, on the FPGA, I think 1 day, depending if you have checkpoints or not, or don't have checkpoints. And then with something that takes days, how are you going to bring up something that interactive? Every time you do a change, you need to do a simulation and wait for 1 day. You cannot run and see what you did was working. And that's the whole gap that we are filling with virtual platforms on the market, and all major companies use virtual platforms these days. So this is a platform that we work on. It's the software guidance for mobile. So we create in ARM a platform that is this is possibly a mobile platform. That's not what you're supposed to do. It's how we would do, and now you choose how you're going to implement. So we create this in hardware, we create this in FPGA, you create this in virtual platform, and I create the virtual platform, and the other guys from OSS, the software, creates the software, and everything is open source. you can go here and download the platforms, the software, and build everything together. So imagine that you need to build a platform and boot this platform with multi-core clusters, a GPU, a global interruption controller, the complete boot I'm going to show you later. And nowadays, all the CPUs, all the big computers have a controlling system. This is a system control processor. It boots the system, it controls the power, it checks if everything's working correctly, and that's how the simulation starts. So have to model all this and then bring up a boot sequence that we starts on EL3, which is the most secure, and have to build all this together until reach your application. I have a better picture here. So this is the sequence by time. So you reset BL0, reset the processor, it starts, then resets the BL1, then the 2, the 3.0, 3.1, 3.2, and 3.3. At the point of you are in the 3.3, you're in the bootloader of your Linux or Android, and you have all these 7 steps to reach this point. This is doable in RTL. We do that, but it takes a long time. And it's not feasible for software development. I cannot develop the newest Android with RTL if it takes days. Everything needs to be faster, and everything needs to be more quickly to change. If there are bugs, we need to quickly fix, and that's not what happens with FPGA in RTL. And that's the whole point of virtual platforms on a commercial environment. So this is another platform we are working to. It's an infrastructure server or networking, depending on how you're using. This one has 96 clusters of the biggest CPU that we have ever released, the V1. Has a mesh connection that has, I think it's 8x6 XPs, and it's very large. It's connected to an MMU, the system MMU. There's a bunch of peripherals, connect here. There's 2 controlling processors. We have the system control processor and the MCP, which is the power controlling. So we have not just the system control, we have power control. So we have a lot of things to model. Everything will be tightly integrated and work. So we need to run all that boot flow and bring up your UEFI and bring up all the servers and have this working together. I think I'm running out of time now. So that was the last example, but I think we can open to questions. And thank you very much for your attention. Thank you very much for inviting me.
Well, thank you, Felipe, for your presentation. It was a very, very nice, very, say, complete presentation, because there is a lot of stuff there. So people in the chat, you are free to ask questions. As you ask questions, I will send them to Felipe. Meanwhile, I had some questions, because I recently started studying a bit of, let's say, virtual platform modeling, something like that. Mm-hmm. So doing very more like studying things than in fact implementing. Like in these platforms, we know that there are memory accesses. The way that you access memory, the way that you implement memory has a huge impact in both performance and power consumption. Mm-hmm. And energy efficiency. So is it possible to model these particular characteristics of, let's say, memory access schemes or something like that, to have an idea how the system will behave in these virtual platforms?
There are several ways that have been studied for a few times. So, for example, on G5, you can have the cache model that's very precise. You can have a cache model that's like hardware, but your simulation is going to suffer 100 times. So if you want to explore how memory consumption or latency affects our application, you can do that with virtual platforms. The problem is you'll be 100 times slower, even though it's 1,000 times faster than System C and 1,000 times faster than the RTL. You can do that with a G5, even with our tools like OVPSync and the fast models, what I work, we have cache models. Mm-hmm. You cannot create cycle precision from nothing, but you can create a cache protocol that emulates the latency, and you have a notion how cycles are going to take, and then you can do your power by area of cache using some tools that are available on the internet, or there are researchers. So you can create that. You just need to think that if I need precision on the cache, on the memory path, you need to know which components are using, and these components are processing, because if you have a very good cache model, okay, that's awesome. But how good is your branch prediction? Because if your branch prediction goes wrong, you have a new reorder buffer fault, and you have to refetch a bunch of stuff. So if your reorder buffer and your branch prediction are good, and you have a good cache model, you can do what you want. But you need to think about the details. That's the difference between working with RTL. In RTL, you have this and works. You do whatever you do, and you have always the same results, the precise results or the golden results. But if you're working with virtual hardware, you need to think the limitations before you start your work, and then thinking how I overcome these limitations, or if I don't overcome the limitations, how I implement a software or a hardware that don't steps on these limitations, and how I go through these limitations, and I get very clear on the paper I have those limitations, because there's a bit first thing people want to say to you.
Yeah, well, that really explains a lot of what's going on. But yeah, in fact, when you go to RTL, like even though you say it's 100 times lower when you have that cache, for sure you're gonna take you will be speeding up your let's say testing or experimentation process, because writing a cache protocol in RTL is not something very trivial. And so while we wait for questions from the audience, this is more general questions. Have you ever worked with these systems? It's a kind of solutions that some CAD companies have, where you have a hardware-based emulation system, like you can emulate them using FPGAs or like platforms specifically for that. Have you ever worked with that?
So our teams are way separated, but I'm more. We have these projects. For example, this project I showed you, the STM775. I do the FPGA, the FEP. Someone does the software. Someone else do the FPGA. Someone else do the RTL. And we have all this same software working different levels, starting with the virtual platform. So I don't work directly, but we work with people that work that. So they can port a big platform to FPGA, but the problem is the size of the platform. So today you have an ARM processor. You should have 8 cores in a cluster. Have GIG controller, SMU controller, GPU controller, and usually doesn't fit in the largest FPGA, so people have to cut stuff. So you can do that. And let's say I have a system that holds inside the FPGA. Now you need to run that thousands of times. You need a farm. And we had people that work in farms. They are good, but it's a farm of FPGAs. If you are working on FPGA in your PC, you know how many times that things breaks and how many times you need to reset things and reflush. Imagine now that you don't have access to FPGA. You need to do that by command line on a server somewhere in the world that you don't have access, and then things crash and the FPGA dies. Who's gonna fix that? So we need to get another FPGA and open a ticket and say it's doable, but it's all in time. So if you want to develop Android, you cannot do on FPGA, but you're gonna run Android on FPGA to know that your features work. And if the features work, then you're gonna move to our RTL. Sometimes in parallel, everything happens in parallel these days, but we're gonna have RTL simulation at the same time, have FPGA and FP simulation. So we do everything FP, move to FPGA, the features you want to explore, and then you move to RTL to just complete and say everything works, and we are ready to go.
Okay. Well, I just have one final question, which was something that in the last system that you were working, which is a very complex system, several cores, IPs, and when you have these, these ones. So let's say you model this in a virtual platform. Let's say this part of all these green parts here. How do you use let's say an in-house model for these IPs, or when you have a specific IP, like let's say the 400 gigabit Ethernet, do you model this in some way, or does the IP already have some, let's say, model for it so that you can embed in the platform, or you don't use that? You don't consider?
So all in green, that things that we are modeling on the FVP nowadays. FVP is fixed virtual platforms, which is the binaries that you can get from free from the website. But this, we have a whole team inside ARM called Fast Models, which they create these C++ models. And usually we have all the ARM models plus some other models. We have a cache model that's our cache, but we don't have a DMC because we don't sell DMCs anymore. But we have a model for DMC and we have a model for Ethernet. I don't think we have a 256 gigabytes high performance because it's a virtual platform. We don't have the concept of queuing in PCI Express. Don't need to have the hardware that do 4 gigabytes. We just need one Ethernet that works, and that abstracts for the software because they just need Ethernet. They don't need to know the speed. It's a simulation. But usually what ARM does, we don't sell, we sell the fast models for some kinds, but usually we sell the models to Synopsys and Cadence. They wrap together inside System C, and they sell them to other clients. So everybody use our models, but they're buying from Synopsys because it's a chain. But this FVP, so this platform here, you can get that from the ARM website for free, and there's whole open source software. You just compile the source, get the binary, you can run this 96 platform. I think it's on the website is 16 or 64, but have a large platforms and have all these components in green.
Yeah, I was just a bit unsure because I know it's an untimed, the part that you said that we don't have, like, it's not a cycle accurate, but still you have a lot of data that you have to process. So, but this is, let's say, given an infinite time, you can process anything, basically. So,
usually you are way faster. So even with Ethernet, we are way faster than anything else. So because you don't have time, you don't know if it's 4 gigabytes or 10 gigabytes. You're sending data as fast as possible on the virtual machine. So the concept of gigabytes per second doesn't exist, but it's super fast because you have access direct to the memory. You're not sending something to another model. You just everything together in a binary.
Okay, then, if we don't have any more questions from the chat, let me just see here. Apparently, we don't. I'd like to thank you for your presentation. It was very, very. I'm sorry for the background noise, and I'd like to thank you for this presentation and for accepting giving this talk to our event. Thank you.
Thank you very much. Thank you very much for inviting. I'm very happy to present.